All right, let's talk about optics. Now, I know what you're thinking, flashbacks to high school physics, right? But forget all that. This is way cooler. This is the story of how we actually see. It's the incredible science that takes just a simple beam of light and turns it into, well, everything you see around you. So think about this for a second. How can the exact same stuff, light, let a scientist see a tiny little microbe under a microscope and also let an astronomer see a galaxy millions of light years away? How does that even work? Well, that's the big question we're going to tackle today. Okay, so here's the secret. The entire vast field of optics, from the mirror in your bathroom to the James Webb Space Telescope, it all boils down to just two basic things light does. That's it. It can either bounce off something, which we call reflection, or it can bend as it passes through something, which is refraction. Literally every optical gadget we've ever invented is just a clever way of mastering these two simple tricks. So let's start with trick number 1, bouncing light. This is probably the one you're most familiar with. It's what happens when light hits a surface it can't go through. It's called reflection. Yeah, the fancy word for it is reflection, and it's pretty much exactly what it sounds like. A ray of light comes in, hits a smooth, shiny surface, like a mirror or maybe the top of a calm lake, and it just bounces right off. It's not getting soaked up, it's just getting sent off in a new direction. And here's the really cool part. This bouncing isn't random at all. Light is super predictable. It follows this one beautiful, simple rule. Whatever angle the light comes in and hits the surface, it bounces off at the exact same angle on the other side. It really is that simple. The angle it comes in is always the angle it goes out. You know, you can think of it like a perfect game of pool. The way the ball hits the cushion is exactly how it's going to bounce off. Light does the same thing every single time. And that perfect predictability, that's everything. Because if we know exactly how light is going to bounce, we can build surfaces that control it. And that's all a mirror is, right? It's just a super smooth surface, designed to organize all those bounces perfectly so they form a nice, clear image that our eyes can understand. All right, so bouncing is pretty straightforward. Now let's get into trick number 2, which is honestly a little bit weirder. This is bending light. This is what happens when light actually passes through a substance instead of just bouncing off of it. I'm sure you've seen this a million times. You stick a straw in a glass of water, and when you look at it from the side, it looks like it's broken right at the surface of the water. Well, get this. That's not an optical illusion. Your eyes aren't tricking you. The light itself is actually bending on its way to your eye. So what's going on? Well, this is called refraction. And here's the key. Light doesn't travel at the same speed through everything. It moves at its top speed in the vacuum of space, but it slows down a little bit when it goes through air. And when it hits something denser, like water or glass, it slows down even more. And it's that sudden change in speed that forces the light to bend, to change its path. You know, the way scientists measure this is with something called a refractive index. But honestly, you can just think of it as a speed limit for light. Every material has one. Air has a really high speed limit, so light barely slows down. Water has a lower speed limit, and something like a diamond has a really strict speed limit. The higher that index, the more the material slows light down, and the more it's going to bend. And of course, once we figured this out, well, that's when things got really interesting. We realized we could shape materials, like glass, into specific curved shapes, lenses, to control the path of light with incredible precision. And this basically gives us two main types of lenses. You've got a converging lens, which is thicker in the middle. It takes light rays and bends them inward, focusing them all down to a single point, like a magnifying glass. And then you have a diverging lens, which is thinner in the middle, and it does the exact opposite. It bends the light rays outward, spreading them apart. So, okay, we can bounce light with mirrors, and we can bend it with lenses. But the real magic, the part that lets us see the invisible, that starts when we combine these two simple tricks to build instruments that see far, far beyond what our own eyes are capable of. And look, when you boil it all down, every single one of these amazing devices, from microscopes to telescopes, is really just trying to do two things. First, magnification, pretty obvious, right? Makes stuff look bigger. And second, resolution, which means seeing those bigger things with clear, sharp details, not just as a giant blurry blob. So, a microscope? It is a masterclass in bending light. It's basically a series of converging lenses, one after the other, working together to take a tiny little object right in front of it and magnify it hundreds, even thousands of times. It literally reveals a hidden world. Now, a telescope has a totally different problem to solve. It's not about making something tiny look big. It's about grabbing as much faint, weak light as possible from something that's incredibly far away. And to do that, it can use lenses to bend the light, or, as we see in a lot of powerful telescopes, mirrors to bounce it. So you might be wondering, why use a mirror instead of a lens? Well, get this. A really big, thick glass lens can actually absorb some of that precious, faint starlight as it passes through, which makes the final image dimmer. But a mirror bounces almost 100% of the light that hits it. That's why the most powerful telescopes in the world are reflecting telescopes. They use gigantic mirrors to give us those stunningly bright, clear pictures of space. Okay, so we've talked about mirrors and lenses and microscopes and these giant telescopes. But you know what? All of this incredible human technology, it's all just an attempt to copy the most amazing, most sophisticated optical instrument ever created, the human eye. And this is the part that just blows my mind. Everything we've been talking about, this whole story of bending and focusing light, it's happening inside your own head right now as you're watching this. Your eye has a lens. It uses refraction to bend incoming light and focus a perfect little image onto your retina. It's a living biological camera performing these incredible tricks every single second you're awake. Which kind of leaves us with this one last pretty deep thought. If all these instruments, even our own eyes, aren't showing us reality directly, but instead are just showing us an image created by bounced and bent light, then how much of what we see every day is actually what's there? It makes you wonder, doesn't it? What does it really mean to see something? Anyway, something to think about.